Chapter 3. Components and Systems. Introduction. Weight Shift Control, WSC. Aircraft come in an array of shapes and sizes, but the basic design features are fundamentally the same. All WSC consist of a flexible wing made with a sail fitted over a rigid airframe. A separate carriage is the fuselage, which consists of the flight deck, propulsion system, and landing gear. Figure 3.1. End of page 3-1. Wing. The wing has a structural frame that the sail fits over. Although the wing structure is rigid, it is designed to move and allow the sail to flex and the wing to deform or warp, to provide a simple control system with no pulleys, push rods, hinges, control cables, or separate control surfaces. This simplifies maintenance and reduces the cost and weight of the wing. Each wing is built from high-quality aircraft parts including alloyed aluminum tubes, stainless steel cables, hardware, and specially designed sailcloth. Wing frame components. The structural frame of the wing is composed of the leading edges, keel, crossbar, pilot control frame, king post, and wires/struts. The wing frame is a number of structural triangles formed by the wing components. These triangles, braced by wires and struts, provide a strong and lightweight frame to support the flexible sail. Figure 3.2. Leading edges. Leading edges are tube assemblies that are at the front of the wing, the leading edges of the wing airfoil. These are swept back to form the front shape of the wing and attached to each other with nose plates. The leading edges support the airfoil and are designed to flex as part of the wing structure. The leading edges are each made up of two main sections, an inboard and an outboard section, as shown in figures 3.2 and 3.3. Additional tubing sleeves are typically used for added strength where the leading edge attaches to the nose plates, and where the inboard and outboard tubes join at the crossbar attachment. This sleeving can be internal or external depending on the specific manufacturer's design. Typically, additional sleeving is used throughout the leading edges at various locations to strengthen and vary the flex for the particular design of the wing. Each manufacturer and make/model uses different internal and external sleeving to accomplish specific strength and flex characteristics. Generally, the inboard sections are stiffer and the outboard leading edge section flexes as part of the flexible wing design. Sleeving is commonly added throughout the aircraft where bolt holes are drilled through the tubing to reinforce it around the bolt hole. The outboard leading edge sections can be removed to pack up the wing into a short pack, which is commonly used for shipping. Figure 3.3. End of page 3-2. Keel. The wing keel is like that of a boat keel, the center of the wing, fore and aft. It attaches to the leading edges at the nose plate and performs a number of important functions. It is the structure where the carriage attaches to the wing, and it is the wing structure that connects the center section of the sail at the keel pocket, discussed later in this chapter in the sail section. The control frame and king post, if so equipped, also attaches to the keel. It also provides structure for the upper and lower wires, if so equipped, and a reference or anchor for the crossbar, which needs some movement in relation to the keel for roll control. The keel is rigid and is not designed to flex, nor is it highly stressed like the leading edges except where the undercarriage attaches to the wing. Sleeving is normally added to strengthen this middle area as well at the nose attachment and rear cable attachments. End of page 3-3. Crossbar. The crossbar is two aluminum tube sections hinged above the keel that attach to the leading edges. The crossbar is tensioned back with the crossbar tensioning cables, which pushes the leading edges forward to conform to the sail. These crossbar tensioning cables are attached at the rear of the keel when the wing is tensioned into flying position. Figure 3.4. These crossbar sections are under a compression load and designed to be stiff with no bending. A larger diameter tube is typically used to avoid any bending when the wing is flying. A ding, dent, or bend in the crossbar could spell disaster during flight because it is one of the main structural members that holds leading edges into position during flight. For wing takedown and packing, the crossbar haul-back cables are released, the crossbar hinged center moves forward, and the leading edges rotate in toward the keel about the nose plates and come together, allowing the wing to fold down into a long tube for transport and/or storage. Control frame. The triangle-shaped control frame serves two main purposes. It provides the lower structure for the wing and is the control bar for the pilot. The control frame is bolted to the keel with two down tubes extending from the keel attachment to the horizontal base tube, which is the pilot's control bar. Figures 3, 2 and 3, 5 and 3 to 6. Control frame corner brackets at the bottom of the down tubes provide the wing structural attachments for the flying cables or struts that attach to each leading edge/crossbar junction, and secure the control bar fore and aft to the wing with the front and back wires attached to nose plates in the aft section of the keel. Figures 3, 5 and 3 to 6. End of page 3 to 4. During flight, the down tubes are similar in compression to the crossbar and must be stiff and straight to maintain structural integrity. The base tube/control bar is under tension during flight. Front and rear flying wires hold the control frame in place fore and aft. Side flying wires hold the control frame in place side to side and provide structure to hold the wings in place while flying. Figures 3, 2 and 3, 5 and 3 to 6. Strutted wings use struts in place of the side flying wires, which is discussed later in this chapter. Training bars are added for dual controls so the person in back can fly the aircraft. These are typically used by an instructor for training but can be used by a passenger in the back also. Figure 3, 7. King post with wires on top wing design. Similar to the lower control frame holding the wing in position during flight, the king post is attached to the keel and supports the upper ground wires which hold the wing in position on the ground in negative loads during flight. Figure 3, 2. It also provides a structure for reflex lines which is discussed later in wing systems. Topless wings with struts. Similar to airplanes with struts to support the wings, some WSC aircraft replace side flying wires with struts, eliminating the king post and ground wires on top of the wing. This provides a number of benefits, but primarily, no king post is needed because the struts can take a compression load and hold the wings up on the ground and also take the negative loads during flight. With struts, a WSC aircraft is much shorter in height, allowing it to fly into hangars with lower doors and ceilings. This can make a big difference in finding a suitable storage for the aircraft if leaving it set up. Figure 3, 8. End of page 3 to 5. Some strutted designs allow the wings to be folded back while still on the carriage. This can also be helpful when using a smaller space for storage by folding the wing up without taking it off the carriage. Figure 3, 9. It is also convenient for sea trikes since the aircraft does not have to be taken out of the water to fold up the wing. Strutted wings have a clean upper surface with no holes required for the king post or wires to go through the top of the sail. This reduces interference drag on the top of the wing. Increasing overall efficiency, no holes in the sail also eliminates any high pressure leakage from underneath the wing getting sucked up to the lower pressure on top of the wing. Figure 3, 10. Sail components. The sail is a highly refined design that integrates with its wing frame. Each sail and wing frame are designed for each other and are not interchangeable with other sails or wings. Modern sails are designed with complex geometry and sewn to precision to achieve a highly efficient design. Because of the flexibility of the wing frame and the modern techniques in sail design, the leading edge can have a curved shape which adds to the efficiency and stability of the wing. Figure 3, 11. End of page 3 to 6. Battens and leading edge stiffener. As discussed in the aerodynamics section, stiff preformed battens are the airfoil ribs that maintain the airfoil shape from the root to the tips. Additionally, a foam or mylar stiffener is inserted in a pocket at the leading edge to keep a rigid airfoil shape between the battens from the leading edge up to the airfoil high point. Double surface wings have additional ribs on the bottom surface that are straight or formed to maintain the bottom surface camber. Sail material and panels. Sail material is a combination of polyester materials designed with different weaves, thickness, and orientation to fit the design mission of the wing. Panels are cut to different shapes and laid down at different angles to provide the stiffness and flexibility where needed for the specific wing design. Automated machines typically cut the fabric to precision tolerances and the panels are sewn together with high-strength thread. Pockets and hardware. Pockets are added for battens and hardware is installed for the wing frame and wire attachments.
Trailing edge liner wires are sometimes added for reinforcement and can be used for tuning.
Battens are held in with a variety of batten ties or other methods unique to the manufacturer. Figure 3.12.
Sail attachment to wing frame.
The sail is attached to the wing frame at the nose and the tips. A keel pocket towards the back of the sail secures the sail to the wing keel.
Figure 3.13.
Cables and hardware. Cables are used throughout the wing frame and sail to hold components in place and act as structure to carry loads. Flight and ground cables are stainless steel and attached to components with tangs or other hardware depending on the application.
Cables are secured at each end with thimbles and swaged fittings.
Figure 3.5 shows detail of typical swaged fittings. A variety of hardware is used for attaching these swaged cable fittings to the airframe.
Each manufacturer has different hardware for wing components.
Figures 3.14 and 3-15.
End of page 3-7. Wing systems. Reflex systems.
As discussed in the aerodynamics section, the trailing edge near the root and the tips must stay up during unusually low or negative angles of attack, figure 2.29, to maintain a positive pitch stability for the aircraft. There are a number of reflex systems used to accomplish this in emergency situations.
Reflex cables. Most wings with a king post use cables to hold the trailing edge up at unusually low or negative angles of attack.
These reflex cables are secured to the top of the king post and attached to several positions on the trailing edge where the battens are located. Different manufacturers have different positions where these are attached, depending on the design of the wing. Reflex cables also provide additional reflex at high speeds because the drag of the wires pulls up the trailing edge, creating more reflex at these higher speeds.
Figure 3.16. Washout struts, tubes near the tips that keep the tip trailing edge up during very low or negative angles of attack. They can be inside or outside the double surface of a wing.
The reflex cables may not go to the wingtip, so washout struts are used to hold up the trailing edge at the tip at very low and negative angles of attack.
Figure 3.17.
Sprogs. For wings using struts with no king post, sprogs are used to keep the inboard trailing edge up in place of the reflex cables. A wire attached to the top of the leading edge holds the sprog up in place.
Figure 3.18.
Pitch control system. The pitch control system is a simple hinge on the keel at the hang point that allows the pilot to push the control bar out and pull the control bar in to control pitch.
End of page 3-8.
This wing attachment is different for each manufacturer, but all designs have this hang point wing attachment so the control bar is always perpendicular to the longitudinal axis of the aircraft.
This raising and lowering of the nose is the pitch control system for the WSC aircraft. Figures 2.7 and 3-19. Roll control system. Control bar movement from side to side controls the roll about the longitudinal axis.
The wing attachment hang point allows the carriage to roll around the wing keel. Thus, it can also be looked at from the carriage point of view. When the control bar is moved side to side, the wing rotates around the wing keel relative to the carriage.
Figures 2.31 and 3-19.
It would first appear that moving the control bar to one side, thus shifting weight to the opposite side, could alone bank the aircraft. It is true that shifting weight to the right would naturally bank the aircraft to the right and put it into a right-hand turn.
However, the weight alone is not enough to provide adequate roll control for practical flight.
As weight is moved to one side, the keel is pulled closer to that side's leading edge. The actual keel movement is limited to only 1 to 2 inches each side of center. However, this limited keel movement is sufficient to warp the wing, changing the twist side to side, as discussed earlier in the aerodynamics section, to roll the aircraft, figure 2.24, by changing the lift side to side. Simply, the shifting of weight from side to side pulls the keel toward the leading edge on that side and warps the wing to roll the aircraft. Besides the keel shifting relative to the leading edges and crossbar, overall roll control is adjusted by the designers to FAA-T the mission of the wing through sail material/stiffness, leading edge stiffness/flexibility, amount of twist, amount of travel the keel is allowed, airfoil shape, and the planform of the wing.
Figures 3.20 and 3-21. Trim systems.
There are a number of trim systems to relieve the control pressures for pilots to FLY at different hands-off trim speeds. Ground adjustable trim allows the pilot to adjust the trim speed of the wing on the ground and remain at one speed during flight, while flight adjustable trim systems can change the trim speed in flight. Ground adjustable trim systems. The most common ground adjustable trim system, and typical of most aircraft, is moving the wing attachment hang point forward for faster trim speeds and aft for slower trim speeds. Each manufacturer has different hardware, but the basics of sliding the carriage wing hang point forward and backward on the keel is similar for all. As an example, moving the hang point at the furthest aft position to the furthest forward position could speed the wing up 20 knots. This in turn moves the control bar position back to a new hands-off trim speed. End of page 3 to 9. Another less commonly used method of increasing trim speed is to increase tension on the crossbar by pulling it back further, slightly increasing the nose angle and reducing twist. This increases the angle of attack, AOA, of the tips, producing more lift, and it lowers the nose to a higher trim speed. This is a typical in-flight trim adjustment for high-performance hang gliders. The roll control is diminished with this faster and stiffer wing. Ground adjustable trim systems are described in the Pilot's Operating Handbook, POH. For each aircraft, different loads may require different pitch settings. In-flight adjustable trim systems. Being able to adjust the trim systems in flight has a number of advantages, as discussed later in the flight sections. A number of in-flight adjustable systems are available with different manufacturers. A common in-flight adjustable trim system is raising and lowering the trailing edge. Raising the trailing edge increases airfoil reflex and slows the wing. Lowering the trailing edge decreases airfoil reflex and speeds up the wing. Typically, a crank on a down tube controls a wire that runs up the down tube to the top of the wing. As a result of moving the crank, the trailing edge wires are raised and lowered and the trim speed changed. Figure 3.22. Hydraulic or electrical systems can move the hang point on the wing for other in-flight trim systems. Figure 3.23. Another pilot-actuated trim system in flight is an elastic system in which the pilot increases tension on the elastic system, which raises the nose for climb and slower flight. Figure 3.24. Carriage. The carriage is a completely separate structure from the wing. Without the wing, the carriage can be driven around if needed. Most of the weight and cost of the WSC aircraft is in the carriage. There is a wide range of carriage designs, from the most simple and basic open trikes to the more sophisticated and complex trikes that integrate cowlings and offer a number of adjustments for the pilot and passenger, resulting in comfort and less fatigue during flying. Generally, the more complex the trike, the more it costs, weighs, and the more power it requires for similar wings. Figure 3.25. Structure similar to the wing, the carriage is designed with a number of structural triangles for optimum strength and minimum weight. Each manufacturer and model have specific details that vary, but the carriage structure is typically a mast, keel, and front tube that form the main triangle components of the carriage structure, with the wing attachment at the top of the mast. A seat frame attached to the mast and keel provides rigidity to the main components while providing structure for the pilot and passenger. Figure 3.26. Landing struts attached to the rear wheels provide structure for the main landing gear, and a front fork provides the landing gear structure for the front wheel. An engine mount attaches to the mast, providing structure for the propulsion system to attach to the carriage. Figure 3.26. Landing gear. The landing gear provides support to the WSC aircraft on the ground and absorbs the shock to reduce the stresses on the pilot and the aircraft during landings. End of page 3 to 11. The landing gear is made up of the front wheel, which has a lighter load and is used for steering, and the main or rear landing gear, which takes most of the load for the aircraft. Figure 3.26. The front steering fork for the nose wheel has footrests attached that the pilot uses for steering the WSC aircraft on the ground. Besides ground steering, the foot controls are similar to driving a car. Left foot pedal is brakes on the ground only, and right foot is throttle and power on the ground and in flight. Figure 3.27. The front fork typically has camber, so it naturally tracks in the direction of travel similar to a motorcycle front fork. For training, a second steering control is installed with a connecting rod so the instructor can sit in back and steer the carriage on the ground using the nose wheel. Figure 3.28. Steering dampers are sometimes used to stabilize the front wheel from shimmying at higher speeds during takeoff and landing. Figure 3.29. The front wheel sometimes has shock absorbers where the tire itself can act as the shock absorber. The front wheel typically has a disc or a drum brake, mechanical or hydraulic. Figures 3.30 and 3-31. A front brake is lighter and simpler than rear brakes, but some carriage brake systems utilize the rear brakes. A parking brake is extremely useful for securing the aircraft on the ground without needing chocks for securing the aircraft before takeoff and after landing. A number of parking brake systems are utilized by different manufacturers. Figure 3.32. The main landing gear is the two rear wheels of the WSC aircraft. Since the center of gravity, CG, is much closer to the rear wheels, most of the weight for the aircraft is carried on the rear wheels for taxi, takeoff, and landings. There are a number of different configurations for the main gear. A conventional configuration has two separate systems for each rear wheel. Each side is two structural triangles, one horizontal and one vertical. End of page 3-12. The horizontal triangle consists of a drag strut from the wheel forward to the keel or forward structure to maintain the wheel's fore and aft position, and the main landing gear strut. Both the main and the drag struts can pivot about the attachment to the keel as part of the shock system. The vertical triangle consists of the main landing strut and the shock strut attached to the wheel and up to the keel structure, figure 3.36. Or other structures such as the engine mount shown in figure 3.33, which houses the compressed nitrogen and oil oleo shock absorber. There are a number of other main landing gear configurations in shock absorbing systems such as wire bracing with bungee cord shocks, figure 3.34, fiberglass or flexible, fiberglass or steel, main gears with no struts, figure 3.35, and any variation of these. Carriages designed for faster speeds may have streamlined landing gear systems. Figures 3.36 and 3-37. End of page 3-13.